Okay, we were discussing some basics, let's say, critical issues related to specific additive manufacturing technologies. And we said that these are important and we should consider all these issues while we are designing some parts for these additive manufacturing technologies. The first one was fixed filament fabrication. We said that the orientation is important, the infill percentage, shrinkage. You may sometimes use the bridging, and for the feature sizes, the nozzle will be the most important factor. So you should be aware of the nozzle diameter and design your parts accordingly. Since, for instance, if the nozzle diameter is 0.4 millimeter, then you cannot have a hole, let's say, less than about 1 millimeter. It will be quite impossible to fabricate. So you need to design your parts such that there is no holes, for instance, less than 1 millimeter, even maybe 1.5 millimeters. This is another issue, as you already know. This is valid for most of the additive manufacturing process, but right now just focus on fixed filament fabrication. As you know, we need to have support structures for the overhanging parts, and if this angle is less than 45, then you don't need to have. If that angle is, this angle is higher than 45, you don't need to have any support. And in the designs, especially you have kind of smoother, let's say, transitions between the planes. If that's the case, you will not have any, let's say, less surface quality on the outer regions. You should be aware of this issue and try to adjust your designs accordingly. Here you see some parts printed after each other, and this angle is actually decreased until this point. And as you see, since they are not using any support, the surface, this region actually facing the table has very low surface quality, since the printer is trying to actually print material in air. That's why this quality is low. But if you look at here, up to this point, it's good enough. But when for the last two ones, we cannot accept. I think here you can see the angle. It's not clear, but I think this should be 45, 50, 55, 60. So this is actually, it should be, let me see, 50, 55, 60, 65, 70. So this is a very huge angle, and you can see the low quality of this surface. This is an example for bridging. As the length of the bridge actually increases, the quality gets worse, as you see. And we don't prefer to have bridges, but in some designs, that might be a nice idea. You can always consider this one. And it's better always keep this bridging length as small as possible. Otherwise, if you have such beads actually hanging in air, this is not actually acceptable. You need to do post-processing, and also the strength of this parts will be lower compared to the cases where you use support structure. But the disadvantage of using support structure is that, as you know, you will be wasting material and wasting your time. This is, again, although it's under FFF, it's valid for most of the additive manufacturing technologies. The applied loads, if the applied loads is in the direction of slices, then you'll be able to carry, or your part will be able to withstand to higher loads. But if your application is perpendicular to the slicing direction, then you can carry less loads. And we have many papers about this, and this is also engineering. By engineering intuition, you can simply say that this one will carry more loads, since we have these plastics in FFF extrudes in this direction. So we don't have any bonding. We don't need to have use bonding forces while we are carrying this weight. But if you look at the right-hand case, in this application, the bonding between the layers is the most important thing, since they are responsible for carrying this load W. Another issue about triple F is that although we are extruding actually circular material, since the cross section of our nozzle is circular, since we want actually our current layer be stick to the bond to the previous layer properly, we need to press it a little bit, and that's why we usually keep the distance between two layers, let's say less than this diameter, which is about the diameter of the nozzle. For instance, if we said that for most of the cases, the nozzle diameter is 0.4, but we don't use layer thicknesses more than 0.4. And this is, with this approach, we make sure that there will be kind of forces. We will pressing these material onto the previous one so that there will be proper bonds between these two consecutive layers. And you should be aware of this issue, since the size of your part will be a bit larger. And these days, actually, for instance, Cura is aware of this issue and they generate their paths accordingly. For instance, you say that the layer thickness should be 0.2, and then it's aware of that. And while extruding material, it actually moves a little bit into the cross section so that once it's pressed, the size of your part will be close to the desired dimensions. For instance, if this is the contour of your slice, and if you simply go over this contour, then that will be the kind of material we are extruding. So the resulting part will be a bit larger than desired. And these days, as I said, there are many computational algorithms, and they are aware of this issue and try to move this path a little bit inside. Assume that this is the modified path. With this approach, once it's pressed, we will have the desired dimension. We will have no material out of this boundary of the original shape. So that's not a big issue, but although you're aware of this phenomenon, sometimes it may not be valid, although you are actually decreasing the size of your inner path, you may still have some extra material out of this boundary. Any questions, guys, about triple F, or any suggestions to these actually rules we should be considering while we are designing parts? Since some of you already have, I think, triple F type of desktop printers, you may suggest more issues, more, let's say, items. No suggestion?
Hocam bazen basarken tabloda kalkma yapıyor. Shrinkage direkt tabloda oluyor.
It's not shrinkage. It's about warpage. It's about thermal stresses, and it's inevitable. And for that purpose, I think you are all know we use kind of a brim. We extrude extra material around the part, especially in the initial layer, so that it's let's say contact area with the table is more than the original case. But it's not about shrinkage. It's warpage. And it's due to the thermal stresses develop at the specific corner, and this happens usually on the longer pieces. But yes, you're right, this is an important issue in triple F and also in other additive manufacturing technologies. Another idea or anything we should be careful about in triple F? Okay, let's go on to the second process, photopolymerization. We talk about it many times that this process is highly useful for very small parts having little features. Its accuracy is much better compared to other technologies. But the problem is that since we are using thermoset materials, thermoset polymers, their strength is not as good as thermoplastics or obviously metals. And we need to use sometimes support structures, as in the case of triple F. And in here, which is somehow similar to the triple F, instead of nozzle diameter, we need to discuss, we need to consider the laser focus diameter. It will determine the minimum feature size. So you cannot have shapes, features whose size is less than the diameter of your laser. And as you know, sometimes if the laser is not powerful enough, you need to make some post curing at the end of the process. There's a question about triple F. Hussein is asking whether can we have weave-like patterns. Yes, it's possible. In one layer, you may have horizontal. In the other layer, you can have vertical layer. There are such settings in most of the CAM software in FDM or triple F. This is an important issue, but we didn't discuss up to now in polymerization, photopolymerization. This is an example of an SLA system. And as you know, we have a kind of a laser underneath. This laser is curing the photopolymer, and polymerization takes place in this tank. And if you have such kind of shapes, here you see this is a kind of a cup-like shape. This is our cross section. And if you try to build in this manner, what will happen? At some point, you will have suction forces, and these suction forces will result in some pressure inside, and there will be cracks initiated, and as you continue, you may break your part. Since due to the pressure inside, since you will have more liquid, more resin trapped in this region, and this will result in cracks and breakage on your part. So that's why it's better if you have such shapes, you provide some kind of escape holes in your design. This is an escape hole, for instance, so that you will not be developing pressure inside. And as you see, once we have a hole here, the printing can be completed without any cracks, but we have a hole here, so you may use an extra part to close it or try to find a solution to overcome this hole. But in summary, the suction forces are important, especially for cup-like shapes. So what do you think? Do we have such an issue if you print this one upside down? Assume that we have the laser upside, but the wet is going downwards. Do we still have this problem?
No.
Yes, we don't have that problem. So this is not an issue for such SLA printers where they're using a platform moving downwards. But if your build plate or platform going upwards and have such cup-like shapes, then you will for sure have suction forces, and you need to handle these forces. And in CAM software of SLA, my printer, there is such a warning. You don't need to worry about it. The software has a kind of an algorithm inside, and it checks your design and sometimes warn you that there might be some forces. Please make a hole here. There are such warnings in the software. So let's talk about selective laser sintering. We know that it's not suitable for metals. You cannot easily do it. It needs lots of post-processing, so we don't prefer to use SLS for metals. Instead, we use, as you know, selective laser melting or some other trademarks. But the main thing is that for metals, we need to melt the powders. And all of these SLS, SLM, or powder-based things happen in a chamber, in a closed chamber, and the quality of the parts are not very good compared to even FDM and SLA processes. Since we are making use of powders, you need to be aware of this issue and maybe do some post-processing if the roughness values are not satisfying your requirements. And in SLS or SLM, other kind of powder-based things, The heating and the cooling are highly important. It's better you do all of these in as uniform manner as possible. Otherwise, you will have some thermal stresses develop. You may have some cracks again initiated due to these temperature differences between some specific regions. And this is one of the biggest challenge in SLS and SLM kind of additive manufacturing processes. But the advantage is, as you know, you can easily produce highly complicated products since the parts are fabricated in a bath, in a powder bath. You don't need to use, especially for polymers, support structures, but for metals, as you remember, in order to dissipate heat, we prefer to have some support structures around the body. With the help of it, obviously you can produce functional designs, moving assemblies. These are all possible with SLS. Let's discuss some critical issues about SLS. Here you see a part that is manufactured in an SLS system. And if you don't have such a hole at the base, since this one is printed inside a belt, it will be quite difficult to remove the powders at the base of this cylindrical part. So this is a nice hole. Once you have it, then with an air jet, we can remove all the powders inside through this hole. Otherwise, you will have some amount of powder actually left in this tank or kind of cylindrical part. Another issue
Hocam
again.
bir şey sorabilir miyim?
Sure, Çağatay.
Mesela buradaki deliği biz dizaynımızda yapmamamız gerekiyorsa yani nasıl bir kaçış yolu bulabiliriz başka?
You may have another one underneath, I don't know, but if you want to remove the powder inside, for sure you need to, but if the powder remaining inside is not a big problem for you, then you don't need to have a hole. So you may just shake it and try to remove unsintered powder, but you don't have a specific solution. You may have a small part and close this hole. This is the simplest solution.
Okay, I understood.
Okay.
Thank you.
Then we have another issue again related to the powder removal. For us to think about this design, we have a kind of a shaft here, as you see, and we said that in SLS it's quite possible to have functional designs, functional assemblies, and this is an example for that. We have a shaft probably. This will be rotating after the assembly is printed. But if that's the case, then you will not be able to remove the powder inside this region. It will be quite difficult since some of them maybe stick to the surface a little bit. You need to apply little forces. You cannot remove them by simply shaking. So that's why we prefer to have such a solution. This gap is increased so that we can apply again some air jet inside and try to remove it. And then we have another hole here. So the excess powder may be actually removed from this hole. This is a simple solution once again, especially for bearing surfaces. It's better you keep this bearing surface as small as possible. As you see in this one, we have such a length, but in the other one, the bearing surfaces are very short. Let's jump to 3DP. Do you remember the other name for 3DP?
Material jetting.
Material jetting or binder jetting? Which one?
Oh, binder jetting. More.
It's binder jetting, three-dimensional printing. It's the abbreviation of three-dimensional printing, and we prefer to use instead sometimes binder jetting, and it's the patent name or trademark name of MIT. They name their technology as three-dimensional printing, but these days we prefer to use binder jetting. And since we are jetting binders, some particles, and also we need to have many post-processing operation, we have a high surface roughness. So if it's highly important for you, then you need to do some machining, other polishing operations should be performed after all these are over in three-dimensional printing. So we may have post-processing, as you know, infiltration is for embedding a secondary material into this printed product. But do you remember impregnation? What is impregnation? So what is impregnation? It's highly similar to infiltration. In the infiltration case, we are embedding secondary metal or secondary material into porous regions. But in the impregnation, we are embedding oil, some lubricants into these porous regions so that the part will be self-lubricating. So, for instance, if you produce a kind of a bushing and do impregnation, then these porous regions will be filled with oil, and in the whole life of the bushing, you don't need to do some lubrication, since it's a self-lubricating part. So that's a nice property. Depending again on your aim, on your application, you may have such post-processing. And obviously, we are aware of this issue. The size of the powders are highly important. They will determine the minimum feature size, which is usually around 50 micrometer or somehow less than that. And since the process is not complete after the part is actually obtained in the printing, we need to do post-processing. The parts are not highly dense as compared to selective laser melting. These are less denser products. There's a question about SLS. Why can we produce metals? You can try, but in sintering, and this is a sintering process, you're not melting the powders. It's quite difficult to obtain a proper product. And then if that's the case, you need to do further furnacing or again, some kind of infiltration processes. So directly, you cannot produce metals on SLS systems. Now let's jump to sheet lamination process. But if you have questions regarding the previous additive manufacturing technologies, I may discuss them. Any questions, guys? Okay. Let's discuss sheet lamination processes. In this process, it's quite difficult to have, let's say, layers less than 150 micrometers, especially for metals, but for papers, we can have it less than that. But once you decrease the layer thickness, then it will be quite difficult to not to actually form the previous layers, since you need to always form one layer or one level. That's quite challenging, especially for papers. But for metals, you need to control the size of your tool. If that's the case, you may try to obtain a bit less layer thickness values. And the advantage of these processes, if you remember, we can embed any kind of structures, sensors, wires, some kind of channels. They are all possible in sheet lamination processes. And for the interior, it's the below regions, you can eliminate staircase issue. And for the outer regions, it's quite possible with you, since you are doing machining operation. You can try to eliminate most of the staircase in sheet lamination processes. And again, since we are using machining, the accuracy, dimensional accuracy is much better. You have less surface roughness. And in this process, bonding is again highly important. Otherwise, while you are doing machining, you may remove one layer from the previous layer. Then we have beam deposition processes, direct energy deposition process, or we can say in such cases, the reflectivity and the conductivity of the metals are highly important, since we are using very high power lasers. And if the reflectivity of the metal is too much, then you cannot concentrate energy into a specific point into your molten pool. That will be quite challenging if your metals have high reflectivities. And that's why people don't prefer to use such metals, such metal powders in beam deposition and other selective laser melting type of metal processes. And we do not prefer to actually use support structures. In some cases, it may be necessary, but it's not preferred. Instead, what they do, they have multi-axis systems. Since they are jetting the powders at very high speeds, they can do also deposition in various angles. This is somehow similar to multi-axis phase deposition modeling. And we talk about it many times that this processes are highly useful for repairing purposes. If you have cracks and other, let's say, wear on a part, then you can put it onto a beam deposition machine and then deposit some powders on these critical regions and try to melt the powders in such regions and repair your product. And we also know that the resolution is one of the worst resolutions we have. The surface quality is again one of the worst, since we have powders moving all around. We have molten pools. Some powders will be actually trapped in these molten pools, and once they are solidified, cooled, we will have some wavery surfaces, and this will result in high surface roughness values. This is actually kind of a summary of the process we discussed. Now I will talk in brief about some specific issues.
Hocam ufak bir şey sorabilir miyim?
Sure.
Bu Poor Resolution Surface'ın işlediğimiz hibrit prosesler haricinde geçerli değil mi? Hibrit proses kullandığımız zaman bunun önüne geçebiliyoruz.
Sure. Since in hybrid processes you have a machining stage. In machining you can overcome this surface roughness problem.
Teşekkürler.
So in considering complex geometry, we were talking about design for additive manufacturing, if you remember. So you need to know all these issues while designing some parts for your additive manufacturing machineries. One of the capabilities, if you remember, is to fabricate complicated geometries. And this is not possible, as you know, in conventional manufacturing. So if it's suitable for you, if it has advantages on your overall design, then you may go with complicated geometries. But if it's meaningless, then it's better again you keep your design as simple as possible. But we are aware of that in any kind of additive manufacturing. In most of the additive manufacturing processes, we can handle complicated geometries. And we said that in SLS or stereolithography, the feature sizes are actually depending on the laser spot size. In FDM, the feature size depends on the nozzle diameter. In other jet printing type of processes, the size of the drops will determine the minimum feature size. And another thing about the complexity, the complexity actually in the Z direction is quite challenging. You cannot have highly complicated things in Z, since we have the layer thickness, as you know, we have bonding between the layers, and this actually limits us to have feature complexities in Z direction. So your features in Z direction can be as thin as your layer thickness, but on the XY plane, your resolution depends on the drops, depends on the laser spot size, nozzle diameter. On the Z direction, your minimum feature size only depends on the layer thickness. But it's better you keep this as several layers thick, not just as one layer thickness. Another important issue about additive manufacturing, as you know, the customized geometries. With any of the additive manufacturing approach, we can have specific parts for individuals. So this is a nice property. If you remember, we discussed this hearing aid and shell. Siemens was using such an approach, customization, mass customization. Depending on the dimensions of individuals' ears, they produce such customized products, and their costs are, if you remember, are very low, and they can do it on the same machine. So they use a single machine. Probably, since the sizes are quite small, they may produce hundreds of these hearing aids at the same time. So in a batch of, let's say, machine, you have 100 products, and these 100 products are not the same. They are belonging to individuals. And we call this one as mass customization. Another important issue in additive manufacturing, as you know, we can easily integrate assemblies. We can have functional products. This will obviously result in complicated parts, but we decrease the assembly time. So if it's possible, always you can try to have such integrated assemblies in your designs that will decrease obviously the production costs and other difficulties during assembly processes. And another advantage this brings that you need to track less number of parts, since if you do kind of a consolidation or if you assemble a single part, all parts into a single product, then you only need to track one part instead of tracking, let's say, 10 parts. That will make your job actually easier. But we know that there are many advantages to additive manufacturing, but the difficulty is that we are all accustomed to the constraints in conventional manufacturing. So that's why it's sometimes quite difficult to remove these burdens on the designers, and you need to always tell these designers that this is possible in additive manufacturing. Please do such kind of consolidation, do assemblies, try to make complicated designs, try to use lattice structures. So you need to change the way actually these designers are thinking, since they are all accustomed to design for manufacturing constraints. But now we don't have such constraints. We have much more freedom in terms of design. So sometimes this becomes quite challenging to change the actually way we are designing. And obviously in design for additive manufacturing, the designers, people don't have to learn many issues about manufacturing. Right now they have fewer constraints and have fewer things to consider while they are designing the products. So if you summarize, actually in additive manufacturing, we have these unique properties. Shape complexity, you can produce any shapes. Hierarchical complexity, you may have small, let's say, features in one part and larger ones at other part of your overall product. You can have functional complexities. You may have even sensors inside your parts, or even you may have material complexity. You may have a transition between different material to another material, or you may have other complexities inside your part. Now we will discuss all these in detail. Let's focus on the first one. But if you have questions, I may try to answer them before we go into the details of these capabilities. You know that in most of the additive manufacturing process, we always say that we can produce any kind of part. But what do you think? In which process we have unlimited part complexity? In FDM, in SLA, in powder-based systems, in deposition, in sheet lamination, what do you think? In which process do we have unlimited part complexity?
I think FDM.
So one FDM, and other answers?
FDM.
Direct deposition olabilir mi hocam?
Which one?
Direct deposition.
So there are many different answers. SLA,
Powder-based.
editing, SLS, FDM. Another, which one is, I think this count the numbers, deposition, SLS. Well, can anyone, for instance, then tell me why, for instance, SLA has unlimited part complexity? Yes, Recep, for instance, you say that SLA has virtual unlimited complexity. Can you tell us why it has such an property?
Hocam ama SLS'te metaller sıkıntı olmuyor muydu yani metal?
But we are not talking about the material. We are talking about the geometry.
Ben onu düşünerek cevap verdim de o yüzden. Çünkü SLA'de de hani direkt photopolymerization yaptığımız için
But
direkt
we are just considering the complexity of the geometry. So,
Hocam bence SLA şeyden olmaz. İçi boş küre yapamayız çünkü içinde reçine olur. O yüzden o bizi constraint'ler diye düşünüyorum. Mesela FDM'de bu çözünebilen supportlarla falan yapılır veya bridging'de içi boş şeyler de yapılabilir diye düşünüyorum.
Tamam,
Ondan
ben de
FDM dedim.
okay. What about SLS? There are some answers about SLS or powder-based things. So why do you think powder-based systems has virtually unlimited part complexities?
The internal supports are easier to remove because they're just powder. If we were to use FDM, for example, we couldn't remove internal supports reliably. But on powder-based, we can just use one simple hole.
Yes, actually, FDM and powder-based systems have more unlimited complexities, but to me, powder-based systems has the highest part complexity. Since think about some assemblies, moving parts, you can try to print them on FDM or FFF, but the thing is that you need to have support structures. For instance, if you have a kind of a shaft and hole, you need to for sure have support structures underneath. But considering powder-based systems, SLS, you will only have powder here, and it's quite easier to remove this powder. So that's why I can say that part complexity is mostly unlimited in powder-based systems, especially in selective laser sintering. So in machining, obviously, we are aware of that. The complexity is actually limited with the tool accessibility. If your machining tool is not accessing anywhere, then you cannot design such kind of things in CNC machining or other kind of machining operations. And on the other hand, if you consider injection molding, usually we have one or two actually mold parts. You need to always consider how we are going to remove this mold. And this again limits our part complexity. But in most of the manufacturing processes, we don't have such limitations. We have mostly unlimited part complexity. In some cases, we have limitations in terms of interior structures, but most of them have higher unlimited part complexity. And another thing in additive manufacturing, the difference between the consecutive parts is not important. You can, for instance, produce a cup in the previous model and then produce another rectangular part in the next step of your or next stage in your machining processes. But considering injection molding, if you want to produce a new part, then that means you need to prepare another mold. In machining again, you may need to design another fixture, change your tool, but these are not valid in additive manufacturing processes. And in additive manufacturing, again, you can have high stiffness and low weight. These are all possible. You can optimize your structures. You can have some very weird lattice structures. These will increase the stiffness, but also they will decrease your overall weight. Here's an example for that. This is a robot ling, and in the initial design, they have material interior, but now with using such a special design, they make use of lattice structures inside and try to reduce the weight, and also they increase the stiffness of the part compared to the initial case a little bit. Actually, you need to compare weight to strength ratio. There's a question about, I think, SLS. We cannot have, yes, you're right to saying you cannot have internal structures in SLS systems. It's only valid in physical position modeling, not valid in other processes. Now let's have a look at other capability, hierarchical complexity. It means that we can have, if you think about, for instance, this part, assume that is quite large, you may have little structures, for instance, at one part. That might be your specific structure, but in other regions of your design, you may have larger designs, larger features. They are all possible in additive manufacturing, and we name this capability as hierarchical complexity. And even with a beam deposition process, special one, laser engine net shaping process, you can have different microstructures. These microstructures can be controlled, tailored with adjusting the size of the laser, adjusting the cooling rate of your molten pool. If you, for instance, decrease your speed, decrease the moving speed of your laser, then that means your cooling rate is low. But if you increase your speed, then you will be increasing the cooling rate. So they are all possible, and with the help of them, you can have different microstructures in specific part of your product and other microstructures in different regions. So this composition is possible with laser engineering net shaping process. It's a direct energy deposition system. And in other conventional products, it's not possible. You can only have a single type of microstructure. You can even do it with extrusion processes, inkjet printer, photopolymer, and other sheet lamination processes. They are all possible ways to have actually hierarchical complexities. Then we have the functional complexity. It's about assemblies. Since you can have, let's say, links between the products, between the specific parts in your assembly, you can easily do it with selective laser sintering. So the joints can be manufactured in the powder bed, and other, even with FFF, you can produce some joints. And furthermore, you can embed some electronic components, some actuators even, and try to make your assembly as complicated as possible in terms of functioning. Here's a weird example, for instance. These guys are the authors of our textbook. They used an SLA printer to print another SLA printer. But the only thing they have done is that since there are some steel components, they embed these components into the printer. So with the help of it, they got a smaller SLA printer by using the original SLA printer. So this is kind of self-replicating printers. And here is another example for functional complexity. You can produce the part and then embed some electronic components onto the part. So this results in a functional product. Then we have material complexities. As you know, we can try to change the composition of the materials in a gradual way or in an abrupt manner. And this is much easier, especially in powder-based systems. For instance, think about, again, beam deposition or direct energy deposition systems. If you have multiple hoppers, they will be jetting different powders, and you can adjust the ratios and have some gradual transition or an abrupt transition between specific materials. And it's also doable if you remember the aerosint example on a powder-based technology. We can do it all with the powders. And by machining, again, if you have some further processes, for instance, think about implants we discussed. In some part of your product, there might be higher surface softness values, but with machining, you can decrease it on another part of the design. And that will help actually, if it's an implant, and the cells will easily adhere to the critical regions, and this will increase the possibility of actually using implants inside the bodies.